Noche Cósmica.
Most people think of time as something absolute, unchanging, a river that flows at the same speed whether you're standing at the bottom of a mountain or floating high above it. But the truth is far stranger. Time doesn't flow at all. It bends, it stretches, it moves at different speeds depending on where you are, how fast you're moving, and how much mass is pulling at the fabric of reality around you. And nowhere does this become more apparent, more profound, than in the shadow of a black hole. Imagine yourself drifting through the silent deep of space. There is no up or down here, no ground beneath you, only the vast and patient darkness, punctuated by the slow wheeling of distant stars. You are utterly alone. Your spacecraft, if you can still call it that, is merely a small, quiet vessel suspended in the void, oriented towards something far away, something invisible, something that pulls at the very meaning of before and after. Your instruments tell you there's a black hole out there, perhaps 10 billion kilometers distant, too far to see with your eyes, too far to feel its gravity as anything more than the gentlest tug at your equilibrium. But you know it's there because the light from its surroundings betrays it. There is a faint glow around it, the last light emitted by matter spiraling downward, growing hotter and brighter as it falls faster and faster toward the edge of oblivion. That light appears almost frozen to your eyes, dimming and reddening, as though the universe itself is holding its breath. And in this moment of observation, you become part of one of the deepest mysteries the cosmos has ever posed, because that black hole, that infinitely dense point hidden behind an invisible curtain, is not simply destroying matter and light, it is doing something to time itself. It is slowing it, stretching it, making seconds last longer for some observers than for others, depending on how close they dare to fall. The closer you venture, the slower your clocks will tick, not because they are broken, but because time genuinely moves differently there. This is not a metaphor. This is not poetic language painting over a more mundane physical truth. This is reality. For more than a century, physicists and philosophers have grappled with this strangeness, this revelation that fundamentally challenged everything humanity thought it knew about the nature of existence itself. And the journey to understanding why this happens, why time slows near a black hole, is itself a kind of journey. It moves backward through history and forward through logic. It challenges assumptions and rewards patience. It is a story that begins not with black holes, but with far simpler questions about light, gravity, and the relationship between them. If you've ever wondered about the deep architecture of reality, about why Einstein changed our understanding of time and space forever, and about what happens in places so extreme that the universe's rules seem to fracture and reform, then this is a journey worth taking slowly. Consider subscribing for more explorations like this one, where we move gently through the universe's most profound mysteries, the ones that reveal how time itself is not a backdrop to reality, but a landscape shaped by mass and motion, woven through with light and silence. But for now, let yourself remain in that moment, suspended, watching the faint glow, feeling the enormity of the question hanging in the darkness. How can time move at different speeds? How is that even possible? These are questions that would have seemed absurd to our ancestors, and perhaps they still feel absurd to us. Yet they are not only possible, they are inevitable, written into the very mathematics that describes our universe. To understand why, we must first understand something older. We must return to a time, that ancient, mutable, flexible thing, when humans first looked at the sky and wondered if time was something they could measure at all. What you're beginning to understand in this moment, as we drift outward from that distant black hole, is something the vast majority of people move through their entire lives without fully grasping, that time itself is not the simple, unchanging river we assume it to be. Time bends, time slows, time moves at different speeds depending on where you are and how fast you're moving through space. And the deeper we venture into understanding this truth, the stranger and more wonderful the universe becomes. If these ideas call to you, if you find yourself drawn to the kind of patient, unhurried exploration of how gravity literally warps the very fabric of time and space, how light itself becomes a prisoner of its own speed, how the cosmos operates according to rules that contradict our everyday intuition, then I'd invite you to subscribe. Here, we take these profound mysteries of physics and astronomy not as abstract equations to be feared, but as stories to be lived and felt. Each slow journey we share together peels back another layer of the universe's strangeness, from the incomprehensibly dense heart of a black hole to the subtle relativistic corrections that keep your GPS working accurately, to the mysterious relationship between entropy and the direction time flows forward. You'll find that the more deeply you listen to how gravity shapes time, the more you begin to see the universe not as a collection of separate objects moving through empty space, but as a single, unified landscape, a continuous fabric of space-time itself, sculpted by every bit of mass and motion within it. Time near a black hole is just one extreme corner of this vast, beautiful, counterintuitive reality. But it's perhaps the most dramatic place to begin learning how much the universe differs from the comfortable stories we tell ourselves about how it works. The path we're about to walk together moves slowly and deliberately. We're not going to rush through Newton's universe, or skip over the quiet revolution that Einstein sparked in the early 20th century, or gloss over the precise experiments that have confirmed these ideas beyond any reasonable doubt. Instead, we'll move through each stage as if we have all the time in the world, because here, in the context of contemplating something as vast as space-time itself, we do. So consider staying with us as we venture deeper into this exploration. There is comfort in understanding that time is not absolute, that it bends and stretches according to predictable laws, that the universe is far stranger and far more interconnected than it appears, and there is profound peace in learning these truths in an unhurried, careful way, surrounded by the quietness of the cosmos itself. For now, though, let yourself settle deeper into this curiosity we've kindled. We're about to travel backward through time, not literally, but through the history of how humanity came to understand time itself. We'll begin in ancient civilizations, where people first looked upward and began to measure the day, the month, the year. We'll see how sundials marked the passage of hours, how the stars themselves seemed to move in perfect, predictable patterns, and in that slow unfolding, we'll discover the seeds of the very revolution that would eventually overturn everything we thought we knew about how time actually works. And in that moment of watching, that patient vigil across the void, we might ask ourselves, what made us so certain that time moved the same for everyone? How did this assumption, so obvious and so wrong, become the foundation of how we understood the universe for thousands of years? The answer lies in the slow, patient way humans learned to measure time at all. In the very earliest civilizations, there were no clocks in our modern sense. There was only the sun, the moon, the stars, a great celestial theatre that played out the same way night after night, year after year. The ancients watched this theatre with profound attention. They noticed patterns, they remembered, and in that remembering, they began to believe that time itself was something constant, something objective, something that belonged not to any individual observer, but to the entire cosmos, ticking away at exactly the same rate everywhere, for everyone. Consider the Egyptian sundial, that simple and elegant instrument that appears in the archaeological record around 1500 years before the Common Era. It was not much, a stick in the ground, a shadow creeping across marked stones, but it represented something revolutionary. It represented humanity's first systematic attempt to divide daylight into measurable units. The shadow moved at a steady pace. The sun rose and set with predictable regularity. From one day to the next, the rhythm remained faithful. What could be more obvious, more universal than this? Time seemed to be a property of the cosmos itself, not dependent on where you stood or how you moved. As civilizations developed, this conviction only deepened. The Babylonians, those brilliant astronomers of the ancient Near East, refined our understanding of celestial motion with astonishing precision. They tracked the wandering planets, those strange stars that moved against the background of fixed constellations. They predicted eclipses. They divided the year into 12 months, the heavens into 12 houses. And underneath all of this careful observation was an unshakable assumption that time was absolute, universal, the same in Babylon as it was in Egypt, as it was in any corner of the world where someone might look up and count the days. The Greek philosophers inherited this certainty. When Aristotle contemplated the nature of time, he did not question whether it flowed at the same rate everywhere. He asked instead what time was made of, how it related to change and motion. For him, and for the tradition that followed him, time was woven into the very fabric of the cosmos. It was not something that varied. It was the container in which all change occurred, unchanging itself. The Islamic astronomers of the medieval period, those patient observers in Baghdad and Damascus and Cordoba, pushed the measurement of time to remarkable precision. Their astrolabes could determine time with an accuracy that would have seemed miraculous to earlier generations. Yet they too worked within the same fundamental assumption, that when they measured the position of a star or the angle of the sun, they were measuring against a universal temporal standard that applied everywhere. When medieval Europe inherited and elaborated these traditions, mechanical clocks began to appear in cities. The invention of the escapement mechanism, a small device that allowed clockwork to tick at regular intervals, was a watershed moment. For the first time, humans could measure time without reference to the sun or stars. A clock in Paris and a clock in Rome could, in theory, be set to run in perfect synchronization. This seemed to confirm what everyone already believed, that time was a universal meter, the same for all observers, independent of place or motion. And why would anyone doubt it? Every person you encountered seemed to experience time the same way. An hour felt like an hour, whether you were at rest or traveling. A day had the same length on a ship or on shore. The aging process seemed governed by the same internal clock. Common sense whispered that time was objective, absolute, woven into the structure of reality itself. It was not something that could be bent or stretched, or made to flow differently depending on where you stood. The development of ever more precise timekeeping, from the pendulum clocks of Galileo and Huygens to the marine chronometers that allowed ships to navigate across the oceans with unprecedented accuracy, only reinforced this conviction. By the 18th and 19th centuries, the idea of absolute time had become so ingrained in human understanding that it seemed almost silly to question it. Time was time, it was universal, it was constant. This was not a hypothesis that required testing, it was simply how the world was. Yet there was something quietly building beneath the surface of this certainty, something that would eventually crack it apart. The more precisely humans could measure, the more carefully they could observe the natural world, the more they began to notice small inconsistencies, tiny anomalies that did not quite fit within the framework of absolute time and universal motion. But those anomalies were still faint, still easy to ignore or dismiss, and the world would continue to operate under the old assumption of absolute time for many more years. For nearly 3 centuries, the picture of time that Isaac Newton painted was so perfectly satisfying, so elegantly simple, that it barely occurred to anyone to question it. Picture him, in the late 17th century, methodically working through the mathematics of motion and force, building a vast architecture of understanding that would hold steady for generations. He saw the universe as something like an immense machine, clockwork, precise, governed by laws that never wavered. And at the heart of this mechanical cosmos lay assumption so fundamental that it seemed almost invisible. Time itself was absolute. Absolute time meant something very particular. It meant that a second passing in London was identical to a second passing in distant India, or on some imaginary point in empty space. It meant that time flowed at exactly the same rate everywhere in the universe, impartial and uniform, ticking forward like the steady pendulum of a grandfather clock that had been wound up at the beginning of creation and would never slow or quicken. There was no relativity to it, no dependence on where you stood or how you moved. Time was simply time, a universal stage upon which all of physics played out its drama. This was profoundly comforting, if you think about it. In a world of constant motion and endless complexity, here was something truly eternal and unchanging. You could measure duration in the same way everywhere. You could speak of simultaneity with perfect confidence. Two events that occurred at the same moment in one place occurred at the same moment everywhere. There was a kind of democracy to Newton's absolute time, a fairness. No observer was privileged. No location was special. Everyone, no matter where they were, experienced time in exactly the same way. Newton himself had felt the weight of this assumption enough to write about it explicitly. In his great work, the Principia, he distinguished between absolute time, what he called true mathematical time, and relative time, which was merely what we measure with clocks and calendars. Absolute time, he wrote, flows equably without relation to anything external. It simply is, he meant to say, part of the fabric of existence itself. And from this simple, profound belief, he constructed equations of motion that described how objects accelerate and decelerate, how gravity pulls at matter, how planets orbit the sun. All of it rested on that bedrock. Time is absolute, uniform, the same everywhere. For most of the 18th and 19th centuries, physics built itself entirely upon this foundation. A clock ticking in your pocket measured something real and universal. The age of the universe was a meaningful quantity because age, duration, meant the same thing everywhere. If you wanted to know if two distant events were simultaneous, you simply compared the time that each event occurred, and if the times were equal, they were simultaneous. It was that simple. The universe had a kind of transparency to it, a clarity born from this universality of time. Imagine watching a master clockmaker at work in his shop, each gear fitting perfectly with the next, each spring wound to just the right tension, everything coordinated with mathematical precision. That was how the Newtonian universe felt to the great minds of the era. Everything made sense. Gravity pulled objects toward each other with a force that diminished with distance. Light traveled outward in straight lines unless something bent its path. Time advanced steadily, the same for everyone, everywhere. The universe was knowable because it was orderly, and it was orderly because time was absolute. This picture was so convincing that even as the 19th century drew toward its close, even as strange new phenomena began to appear in laboratories and observatories, phenomena that didn't quite fit the Newtonian mold, most physicists retained their faith in absolute time. They felt certain that whatever mysteries arose, they would resolve into patterns consistent with Newton's great scheme. Time might be mysterious in some ways, but its fundamental nature, its universality, seemed beyond question. It seemed like bedrock. It seemed like truth. And yet, there was something troubling beginning to emerge. Experiments with light were starting to reveal cracks in this perfect edifice. though the cracks were so small and so strange that it took a while for anyone to take them seriously. Something about the speed of light seemed to resist Newton's own elegant equations of how speeds combine and how motion adds together. But that unease would take time to grow, to spread through the physics community, to finally demand that someone, a young man in a patent office, thinking deeply about trains and beams of light, would be brave enough to question the foundation itself. For now, though Newton's clockwork universe reigned, time was absolute. It flowed the same everywhere. Everyone, from the nearest star to the farthest galaxy, from the highest mountain to the deepest ocean trench, experienced time in exactly the same way. This was the world as most physicists understood it, and it was a world that made sense. It was a world where your intuitions about time, your everyday experience of moments passing at a steady rate, seemed aligned with the deep mathematical truths of the cosmos. Time was universal, reliable, unchanging, or so it seemed. And yet, as the 19th century drew toward its close, something strange began to whisper through the laboratories and lecture halls of Europe. It was not loud, it was not obvious, but it was persistent, like the creaking of old wood in a house that has stood firm for 200 years, and physicists began to notice that something wasn't quite right in Newton's ordered universe. The trouble, it seemed, had to do with light itself. For centuries, light had been treated as something straightforward enough, a wave perhaps, or a stream of particles, propagating through some invisible medium that filled all of space, a substance physicists called the luminiferous ether. This ether was the stage upon which all of light's motion played out, the great cosmic stage that Newton had never quite addressed, but which everyone simply assumed must be there. Without it, what would light wave through? Empty space? That seemed almost nonsensical. But there was a peculiar puzzle embedded in this elegant picture, and it began to gnaw at the minds of the most careful observers. If light traveled through the ether as waves travel through water, then surely the speed of light should behave like any other speed. If you were moving toward a source of light, the light should appear to come toward you faster. If you were moving away, it should seem slower. This was how the world worked. This was how ordinary motion added up. It was called the principle of relative velocities, and it felt as natural as breathing. Except that experiments kept suggesting something impossible. In 1887, two American physicists named Albert Michelson and Edward Morley conducted one of the most famous and carefully crafted experiments in the history of science. They built an instrument of extraordinary precision called an interferometer, and they used it to measure the speed of light traveling in different directions. The Earth, after all, was moving through space as it orbited the Sun. So surely, they reasoned, they should be able to detect a difference in light's speed depending on whether they were measuring it in the direction of Earth's motion or perpendicular to it. The light traveling with the Earth's motion should seem slower relative to the ether. The light traveling against Earth's motion should seem faster. They found nothing, no difference at all. The speed of light remained constant, always the same, no matter which direction they measured it, no matter how the Earth moved beneath their feet. It was a simple result, a clean result, and it was deeply fundamentally troubling. Other physicists repeated the experiment. The result held. Light's speed, approximately 300,000 kilometers per second, was not relative to the observer's motion. It was absolute, constant, invariant. This seemed to violate everything physicists understood about how the world ought to work. How could you have a wave without a medium? How could something move at a fixed speed relative to all observers, regardless of how those observers themselves were moving? It was like saying that no matter whether you were standing still or running, a thrown ball would always travel at exactly the same speed. It defied intuition. It defied Newton. And yet the evidence was there. quiet and persistent, accumulated through careful measurement and repeated verification. The ether, that invisible sea that everyone had assumed must exist, became harder and harder to detect. Perhaps it was very thin, very tenuous. Perhaps it had properties no one had imagined. But the deeper physicists looked, the less they found. A kind of intellectual unease settled over the physics community. There was no crisis yet, no sense of panic. The Newtonian framework had worked beautifully for 200 years. It had explained the motion of planets, the falling of apples, the swing of pendulums. The contradictions seemed small, almost marginal, the sort of anomalies that might eventually be explained away once physicists understood light a little better, once they refined their instruments further, once someone came up with a clever modification to Newton's theory that could accommodate these strange, stubborn measurements. But somewhere in this fog of gentle confusion, a young Swiss-German student named Albert Einstein was beginning to think about these very problems with an intensity that would eventually reshape the entire landscape of how humans understand time itself. The discomfort that others felt vaguely, almost peripherally, was becoming for him a central obsession. What if light's constancy was not a mistake or a puzzle to be solved away? What if it was telling us something fundamental about the nature of reality itself? The stage was set. The old certainties were beginning to crack. And in the space between what Newton had promised and what nature seemed actually to be doing, something revolutionary would soon be born. In the late 1800s, a boy sat in a gymnasium in Munich, and something in the way light moved through the world began to trouble him. Albert Einstein was restless in the traditional schooling of his time, uncomfortable with authority and rote memorization, and yet his mind was already drifting toward questions that would reshape how all of humanity understood the fabric of existence. He would close his eyes and imagine things. A beam of light, he wondered. What would it look like if he could ride alongside it? If he could move fast enough to match its speed, would the light appear frozen? Would he see it as a motionless wave, a snapshot caught in space? This was the seed. Not a calculation yet, not a formal theory, but the patient, almost dreamy questioning of a young person who had learned to trust the voice that whispered in the quiet moments. By his 20s, Einstein was working at the Swiss Patent Office in Bern, a city of quiet streets and old clock towers, and his day job involved evaluating technical inventions. But in his spare hours, he thought, he read the papers circulating among physicists about light, about the ether, about the growing contradiction that puzzled everyone. Maxwell's equations said light moved at a fixed speed. Newton's universe said that motion was relative, that speeds added and subtracted. These two truths should have lived comfortably together, and yet they did not. Something had to give. There were perhaps 5 or 6 physicists in the world who deeply grasped the tension, but Einstein, then unknown, then nowhere, working in a patent office, he intuited something deeper. The problem was not with light, and it was not with Newton. The problem was with time itself, and this is where his mind performed a kind of magic. What if time were not absolute? What if simultaneity, the very notion that 2 events happening far apart could occur at the same moment, was not a given truth, but a matter of perspective? What if 2 observers moving relative to one another would disagree about whether 2 distant lightning strikes occurred simultaneously, not because one of them was wrong, but because the universe itself had no preferred vantage point from which to judge? Imagine standing on a train platform, watching 2 lightning bolts strike the rails far to your left and far to your right at the very same instant. You are sure they were simultaneous. Now imagine an observer on a train moving swiftly away from you, and from their perspective, the train itself carries them forward as the light from both strikes travels toward them. Because they are moving away from one bolt's light and toward the other, the light reaches them at different times. Did the lightning strike at the same moment for them? No, and neither observer is mistaken. The events simply were not simultaneous in the train passenger's frame of reference. This was not mere philosophy. This was the structure of nature itself. And when Einstein worked through the mathematics, patiently, sometimes on his own time, sometimes in conversations with his friend Michele Besso during their walks through Bern, he found that if simultaneity was relative, then time intervals were too. Time was not the same for all observers. It depended on motion. The leap took him several weeks, perhaps months of sustained thought. He would read a paper, then set it aside. He would walk. He would think about light again. He would consider the constancy of light's speed and what it really meant if you took it seriously, not as an approximation or an oddity, but as a bedrock principle. And then, in June of 1905, he wrote his paper on special relativity. It was only 30 pages. It contained no photographs or diagrams. It read almost like a meditation, moving slowly from one postulate to the next. The young patent office clerk had done something remarkable. He had listened to a question and followed it into the dark until light emerged on the other side. He had not added new mathematics to the world, though the implications were vast. He had simply asked a different question. Not how fast can light travel, but what must be true about space and time if light's speed never changes. And in answering that single, patient question, he had begun to undo Newton's 300-year-old picture of time as a universal river flowing equally everywhere. He had shown that time was woven into the fabric of the universe itself, that it bent and stretched, depending on how fast you moved, where you were, what forces pressed upon you. He did not yet know about gravity's role. That would come later, a deeper layer still, but the foundation was laid by a young mind willing to sit with an uncomfortable paradox until it revealed its secret. Imagine a train moving through the night, not racing, but steady, constant. A man sits inside, watching a pocket watch in his hands, its second hand ticking with the same rhythm it always has. Outside, on a platform beside the tracks, a woman stands perfectly still, her own pocket watch glowing faintly in the darkness. Both watches are identical. Both were synchronized before the train began its journey. And now, as the train glides forward through the darkness, something extraordinary happens, though neither the man nor the woman would notice it in any single moment. The man's watch, the one in motion, is ticking slightly slower than the woman's watch, which rests motionless on the platform, not by much. At the speed a train travels, the difference is invisible, smaller than the grain of sand on a beach. But it is real, it is measurable, and it is the first hint of a truth that will reshape everything we thought we knew about time itself. This is the essence of time dilation, born from motion alone, and it emerges directly from Einstein's special relativity, that elegant revolution that began with a simple question: what if the speed of light is truly the same for everyone, no matter how fast they themselves are moving? Think of light as a messenger that always travels at exactly the same speed through the vacuum of space. Always. Nothing faster. This was a revolutionary idea, because it seemed to violate everything the classical world had learned from Newton. In Newton's universe, speeds simply added together. If you were on a train moving at 50 miles per hour and threw a ball forward at 30 miles per hour, someone watching from the platform would see that ball moving at 80 miles per hour. Simple, intuitive. The math worked for everything, until light entered the picture. Einstein asked, what if light doesn't follow that rule? What if, no matter how fast the source is moving, light always emerges at the same speed in all directions? This wasn't merely a mathematical curiosity. It was a constraint so profound that it demanded the very nature of time and space reorganize themselves to accommodate it. Here is where the imagination must slow down and inhabit a strange new landscape. Time, it turns out, is flexible. It is not the same for everyone. If you move through space, time moves more slowly for you relative to someone who is stationary. This is not metaphor. This is not poetry disguised as science. It is a phenomenon that has been measured, tested, confirmed thousands upon thousands of times. Picture two observers again, one aboard a spacecraft moving at a significant fraction of the speed of light, another on Earth, watching that spacecraft recede into the distance. From Earth, the observer sees the spacecraft's clock running slow. The astronaut on the spacecraft experiences nothing unusual. Her clock seems perfectly normal to her. But to the person on Earth, she is aging more slowly. Her clock is ticking more slowly. She will arrive at her destination, having experienced less time, fewer heartbeats, fewer breaths than her twin sister on Earth. The faster you move, the greater this effect becomes. As you approach the speed of light, time dilation becomes more and more dramatic. At 99% of light speed, time inside your spacecraft might slow to a crawl compared to stationary observers. A journey that takes decades for you might take centuries for everyone left behind on Earth. But you never notice the difference inside the spacecraft. To you, everything feels perfectly normal. Your heart beats at the same pace. Your thoughts move at the same speed. Only when you return to Earth and reunite with your stationary twin do the discrepancies become startlingly visible. One of you has aged far more than the other. Why does this happen? The answer rests in a beautiful principle, the constancy of light's speed. If light always travels at the same speed, and if you are moving relative to a stationary observer, then the only way for both of you to measure light as moving at the same speed is if time itself changes. Einstein realized that space and time are not separate, immutable containers in which events occur. They are flexible, they stretch, they compress, they bend in response to motion, and later, as we shall see, in response to gravity itself. Consider light moving through the spacecraft. From inside the spacecraft, it travels at light speed. From Earth, it also travels at light speed. For both perspectives to be true, and they must be, because light speed is universal, time inside the spacecraft must run differently than time on Earth. This is not a weird quirk of measurement. It is a fundamental fact about how reality is constructed. The amount of time dilation depends on velocity, and it is described by a mathematical ratio called the Lorentz factor. But rather than drowning in equations, imagine it this way. The faster you move through space, the more slowly you move through time. It is as though motion and the passage of time are linked by a cosmic balance. You cannot travel faster through space without traveling slower through time. There is only so much motion possible in the universe, and you must distribute it between space and time. This is perhaps the deepest insight of special relativity. Time is not separate from motion. Time and motion are woven together in the fabric of reality itself. Now hold this idea gently in your mind. Let it settle. You do not move faster and slower simply through space. You have also always been moving through time at a constant rate. Stationary or in motion, you move through a combination of space and time. The faster you go through space, the slower you go through time. It is not punishment or reward. It is simply how the universe balances itself. This principle, born from Einstein's meditations on light and simultaneity, sets the stage for something even more profound. For gravity, as it turns out, creates the same effect. A massive object warps space-time itself, creating a dilation of time even more dramatic than simple motion alone. And it is in this gravitational realm, in the intense geometry of twisted space-time near a black hole, that time dilation reaches its most extreme and most beautiful expression. And yet, in the very center of this realization, that time itself could stretch and compress depending on how fast you were moving. Einstein sensed something incomplete, something almost too clean, because there remained one force he had not yet woven into his web of relativity, one ancient presence that seemed to slip between the threads of his new understanding. Gravity, that quiet force that keeps us anchored to the earth, that holds the moon in its orbital dance, that seems to pull us downward with such inevitable, unwavering certainty. For nearly a decade after special relativity, Einstein turned his mind toward this puzzle. How could gravity fit into a universe where time and space themselves were woven together, flexible, responsive to motion? And what he discovered, in that patient, almost meditative fashion of his later thinking, was something far more profound than anyone had imagined. Gravity, it turned out, was not a force at all. Not in the way Newton had described it, not as some invisible hand reaching across empty space to tug on distant objects. Instead, gravity was something gentler, more fundamental, more strange. It was the very shape of the world itself, the curvature of space and time together. Imagine, if you will, a vast elastic sheet stretched taut and smooth before you. Picture it in slow motion, absolutely still, perfectly flat. This sheet is space-time itself, the fabric that contains all of reality, all motion, all possibility. It is smooth and uniform and level. Now picture a heavy ball, impossibly heavy, dense with all the mass of a star, being placed slowly, very slowly, onto the center of this sheet. Watch as the sheet accepts the weight. The fabric dimples, it sags. It curves downward around the ball in a gentle bowl, smooth and continuous, radiating outward in gentler and gentler undulations until it flattens again at the edges. This is not a force. There is no arrow of attraction pulling the fabric inward. There is simply curvature. There is shape. There is the response of the fabric itself to the presence of mass. And now imagine a smaller object, a marble, rolling across this curved surface. It does not fall toward the heavy ball because it is being pulled by an invisible force. It falls toward the heavy ball because that is the shape of the landscape beneath it. The curvature of the surface itself guides its path. This, then, is gravity, as Einstein came to understand it. Not a pull across the void, but the inevitable geometry of a universe shaped by mass. Wherever matter gathers, wherever density accumulates, the fabric of space-time curves around it, and everything else, light, planets, you and I, must follow the contours of that curvature. We are not being pulled. We are traveling along the straightest path available to us in a universe that is no longer straight. But here is where the revelation deepens, where the implications begin to unfold like the petals of some ancient flower blooming in darkness. If gravity is simply the curvature of space-time, and if time is woven into that very fabric that curves, then gravity must affect time itself. The deeper you are in a gravitational well, the more sharply the fabric curves around you, the more profoundly space and time are warped together. And in that warping, in that bending and reshaping of the temporal dimension itself, time must behave differently. Time, in a sense, must flow differently. The implications are staggering, and yet they emerge so naturally, so inevitably, from this simple picture of space-time as a curved landscape rather than a container. It is as if we had been asking the wrong question all along. We had been asking, how does gravity reach across empty space? When we should have been asking, what is the shape of space itself? Einstein's answer to that second question reshaped our understanding of reality entirely. Space and time are not separate. They are not fixed or universal. They are dimensions of a single fabric, and that fabric responds to the presence of mass by curving, by warping, by reshaping itself. This curvature is what we experience as gravity, and this gravity, this simple bending of the world's geometry, is also what causes time to slow, to stretch, to flow at different rates depending on where you are and how massive the objects around you are. Think of it this way. Imagine standing on flat ground, watching that curved sheet we described, watching how the marble rolls toward the heavy ball. You yourself are also on that sheet, though the curvature around you is gentler, less pronounced. The earth beneath your feet creates a tiny dip in space-time, a gentle slope. The sun creates a much larger one, a vast bowl around which the earth orbits. And a black hole creates something far more extreme, a singularity of curvature so sharp, so profound, that space-time becomes almost torn open, and time, woven into that fabric, becomes almost frozen at the edges of that abyss. Not frozen in place, but frozen in flow, ticking more slowly, stretching out, approaching stillness as you approach the point of greatest curvature. This was Einstein's great insight, arriving fully formed in 1915 in the equations we now call general relativity. Gravity is not a force, it is geometry. And where geometry bends, time must bend with it. Imagine now that you are standing at the foot of a tall building, and somewhere high above you, on the roof, a friend holds a precise clock. Both of you have identical instruments, ticking at exactly the same rate, synchronized down to the billionth of a second. You might expect that as time passes, both clocks would age the same, that your friend's clock and yours would remain forever in step, counting the same moments, the same hours, the same years. But here is where the universe reveals something almost bewildering. They will not. The clock at the top of the building, further from the Earth's center, will tick slightly faster than the clock in your hands. Time itself flows at a different rate, depending on where you stand in a gravitational field. Gravity, you see, does not just pull things downward, it warps time. This idea, gravitational time dilation, is perhaps the most intimate and verifiable consequence of Einstein's realization that gravity bends space-time. And what makes it so profound is not that it is theoretically elegant, but that we can actually measure it. We have measured it, with exquisite precision and repeatability. In 1960, two physicists named Robert Pound and Glenn Rebka stood in the Jefferson Laboratory at Harvard University with a problem they wanted to solve. They had access to a tower of pure iron, roughly 85 feet tall. They took an extremely precise radioactive clock, a cobalt-57 nucleus, capable of emitting gamma rays with a frequency so stable it could serve as the most accurate timekeeper imaginable. They sent this nuclear clock up the tower and kept an identical one at the bottom. Then they waited and listened. What they were measuring was extraordinarily subtle. In a vertical distance of 85 feet, the height of a modest building, the difference in gravitational strength between the bottom and the top is minuscule by any everyday standard. The gravitational field of the Earth is not changing dramatically over such a small distance. And yet, the timekeeping rate did change. The clock at the top ticked faster than the clock at the bottom. The difference was tiny, a few parts in 10 to the 15th, but it was real and measurable. How does one measure such an impossibly small difference? Pound and Rebka used a technique involving the Doppler shift of light. When the gamma rays from the upper clock traveled downward toward the lower detector, the photons were falling toward a region of stronger gravity, and this fall actually gave them extra energy, a gravitational blue shift. Meanwhile, the rays from the lower clock traveling upward had to fight gravity, losing energy and shifting toward red. By precisely tuning the frequency of one clock and observing the difference in how these shifted rays were absorbed, Pound and Rebka could detect the time difference. The universe was keeping score, and the score was clear. Gravity slows time. The deeper you sit in a gravitational well, the slower your clocks tick relative to someone further away. Or, to reframe it in a way that might feel even more strange, if you were able to descend into stronger and stronger gravity, you would age more slowly. Your heartbeat would slow, your thoughts would slow, not because your body would notice anything different. From your own perspective, time would feel perfectly normal. But to someone watching you from far away, in weaker gravity, your entire life would appear to unfold in slow motion. You would become a kind of biological time traveler, moving forward through years while they moved forward through decades. This is not metaphor or poetry, it is measured fact. Modern atomic clocks are so sensitive that if you carry one up a tall building, ride an elevator to the top, and bring it back down, the clock that rode upward will have aged slightly more than its twin that remained below. The effect accumulates. An airplane flying at cruising altitude ages measurably faster than someone standing still on the Earth's surface. An astronaut aboard the International Space Station, orbiting at high altitude where gravity is slightly weaker, ages fractionally faster than their family members on the ground. These differences are tiny in human terms. Over a whole year, the difference might be only a fraction of a millisecond, but they are real. The reason Pound and Rebka's experiment mattered so deeply was not because it surprised anyone who understood Einstein's equations. The math had predicted this effect with perfect precision decades earlier. Rather, it was the first time humanity had directly, experimentally confirmed that gravity and time were entangled. It shattered any lingering notion that time was somehow separate from the material world, floating above it, untouched by mass and energy. Time was not a stage upon which physics played out. Time was part of the fabric itself, woven together with space and matter and gravity into one unified whole. And that fabric could be stretched and compressed, warped and curved by the presence of massive objects. Consider what this means as you contemplate the cascade of gravity near something far more massive than the Earth. The stronger the gravitational field, the more extreme the time dilation. Near a neutron star, so dense that a teaspoon of its material would weigh 1 billion tons on Earth's surface, time would slow to a crawl relative to someone in empty space. Near a black hole, where gravity does not merely slow time, but seems to bring it almost to a halt, the effect would be orders of magnitude more profound. But before we venture all the way to that extreme, it is worth lingering for a moment in quiet recognition of how strange and wonderful it is that something as seemingly immaterial as time should be beholden to something as tangible and mundane as gravity. They are not separate realms. They never were. Now imagine what happens when gravity becomes so extreme, so overwhelmingly powerful, that space-time doesn't merely bend around a massive object, but begins to curl back on itself entirely. This is where our understanding of the universe encounters something that seems almost impossible, yet is woven into the very fabric of Einstein's equations as naturally as light bending around the sun. Black holes are, in essence, the universe's most perfect expression of curved space-time, the final destination of what happens when matter becomes so densely packed that escape itself becomes impossible. Picture, if you will, a star far more massive than our Sun. For most of its life, it exists in a kind of balance, a slow equilibrium between two opposing forces. The outward pressure of nuclear fusion deep in its core, that ancient process where hydrogen fuses into helium and releases tremendous energy, pushes constantly against the inward crush of the star's own gravity. As long as that fuel burns, the star remains stable. It has been burning for millions or even billions of years, shedding light and heat into the cold night of space, and in doing so, it has kept itself suspended in this delicate balance. But stars are mortal things. The fuel doesn't last forever. And when a truly massive star, say 20 or 30 times the mass of our own Sun, begins to run out of its nuclear material, something begins to shift. The outward pressure weakens. The collapse starts slowly at first, then with gathering speed. The core contracts, becoming hotter and denser with each passing moment. And as it contracts, the curvature of space-time in that region becomes ever more severe. The fabric of space-time, already bent and warped by the star's original mass, begins to pinch inward. It's as though the entire cosmos is holding its breath. In those final moments before collapse, something extraordinary unfolds. The star's outer layers may blow outward in a violent supernova explosion, one of the brightest events in the universe. But the core, the heart of the star, continues its relentless compression. The electrons that normally maintain the structure of atoms are forced into the protons, creating neutrons. The density becomes almost incomprehensible. A teaspoon of this neutron star material would weigh as much as a mountain on Earth. And yet, if the original star was massive enough, even this incomprehensible density is not enough to stop the fall. The collapse continues. The curvature of space-time intensifies further. Gravity no longer merely bends light and slows time in the manner we've come to understand. Instead, something stranger begins to occur. The space-time curvature becomes so acute, so singular, that it creates a true boundary in the fabric of reality itself. This boundary is called the event horizon. Think of it this way. Space-time is like an ocean, and the collapsing core of the star is creating a whirlpool of infinite depth. Near the center of that whirlpool, the curvature becomes so steep that even light, the fastest thing we know, traveling at its maximum speed, cannot escape. If a beam of light were to venture past a certain distance from this point of collapse, it would find itself pulled back toward the center, no matter how much energy it possessed. That distance, that invisible circle or sphere, depending on your perspective, is the event horizon. Nothing that crosses it can return to the outside universe. Not matter, not radiation, not information, nothing. And within the mathematics of what Einstein gave us, beyond that boundary lies the singularity itself, a point of infinite density. A mathematical point in space-time where our equations break down entirely, where the curvature becomes infinite, where all the mass of the collapsed star is crushed into a space so impossibly small that our current physics can offer us no description of what is actually happening there. It is a place where gravity has won so completely that space-time itself seems to tear. What is remarkable, what asks us to sit quietly with the strangeness of it all, is that none of this violates what we know. Black holes are not anomalies in Einstein's theory. They emerge from it. They flow naturally from the equations. When we write down the mathematics of how space-time curves around mass, and we allow that mass to become sufficiently concentrated, black holes are not an unexpected consequence. They are an inevitable one. They are what the equations tell us must exist. The collapse happens quickly in cosmic terms, perhaps over the course of a few seconds for the core. But here is where time itself enters this final drama in the most peculiar way. If we imagine standing at a safe distance, watching this collapse unfold, something astonishing occurs. As the star's material falls toward the event horizon, the light that it emits becomes increasingly redshifted. The electromagnetic radiation stretches, the frequency drops, the brightness fades. From our distant vantage point, the collapsing star appears to slow down. The fall seems to become more and more sluggish. Clocks on the surface of this collapsing material tick slower and slower from our perspective. And time itself, that river we thought flowed uniformly throughout the cosmos, appears to nearly freeze as the material approaches the event horizon. This is not an optical illusion or a trick of perception. It is time itself, actually flowing more slowly in that intense gravitational field. The closer you approach the point of infinite curvature, the more severely time dilates. The stronger gravity becomes, the slower clocks tick, and the more alien the experience of time becomes. This is the phenomenon we now prepare to understand in its fullest expression. Imagine now that we draw closer, not physically but in our minds, to the absolute edge of this cosmic abyss. There exists around every black hole an invisible boundary, a threshold that marks the point of no return, and this boundary carries a name that has become almost mythological in physics: the event horizon. It is not a wall you could touch, nor a surface made of anything material. It is something far more profound, a line drawn by mathematics and gravity itself, where the rules of escape change forever. To understand what the event horizon truly is, we must think carefully about what it means to escape. In your everyday world, if you throw a ball upward from the Earth's surface, it will slow as it climbs, eventually stop, and fall back down. But if you threw that ball with enough velocity, with what physicists call escape velocity, it would never stop. It would continue upward forever, slowing as Earth's gravity tugged at it, but always moving away, always winning against the pull. The faster you throw, the slower it climbs, but it still escapes. Now imagine a world where the gravity becomes so intense that no matter how fast something travels, no matter if it moves at the speed of light itself, the fastest thing the universe allows, it still cannot escape. That is the world inside the event horizon. The event horizon marks the radius at which escape velocity equals the speed of light. And because nothing can move faster than light, nothing that crosses into this boundary can ever leave it again. Not a particle, not a beam of radiation, not even information itself can ever emerge from within. It is a one-way membrane, a cosmic membrane, that the universe draws around its most extreme objects. But here is where time enters this story, with profound strangeness, and why we have been building toward this moment all along. If you were watching from a safe distance, say, orbiting at a comfortable remove, observing a black hole through a powerful telescope, you would see something that defies intuition. You would watch an object falling toward that event horizon, and as it fell deeper and deeper into the gravitational well, that object would seem to slow. Its motion would appear increasingly sluggish. The light it emitted would shift deeper into the red, dimmer and dimmer and dimmer, as if the universe itself were turning down the brightness. And here is the crucial part. From your distant vantage point, that object would never actually reach the event horizon. It would appear to freeze at the boundary, suspended there forever, slowing infinitely but never quite crossing that final threshold. Time itself, as seen from your perspective, would appear to stop at the event horizon's edge. This is not an illusion, though the word illusion itself might mislead us. It is a real effect of how gravity shapes time. The clocks of anything falling toward the event horizon do tick more slowly and more slowly as they approach, and the ticking slows without limit as that threshold draws near. From the outside, an infinite amount of the universe's time would pass before that object reached the edge. Eons would unfold, stars would be born and die, civilizations might rise and fall, and still that falling object would hang there at the boundary, caught in an eternal moment as seen from afar. Yet this is only part of the story, and here the universe reveals one of its deepest asymmetries. What you would see from your orbit, this frozen, slowed object suspended at the edge, is not what that falling object would experience from its own perspective. This is a truth so strange that it took our minds generations to accept it, and even now it carries a dreamlike quality. An object actually falling into a black hole would not feel itself slowing. According to its own experience, its own clocks, its own sense of time passing, it would cross the event horizon and move inward at a perfectly normal pace. It would not encounter any dramatic wall or barrier. There would be no sudden jolt, no moment of impact. It would simply cross that invisible boundary as if passing through air, experiencing nothing remarkable at the moment of transition itself. Time, from its perspective, continues to flow at its ordinary rate. It is only your distant view of it that shows the slowing. This asymmetry sits at the heart of relativity, a reminder that time and motion and the passage of moments are not absolute cosmic truth, but rather perspective-dependent experiences. What one observer measures is not what another observer measures. What one clock reads differs from what another clock reads, and at the event horizon, this divergence reaches its extreme. The universe has two perfectly valid truths about a single object, and which truth you experience depends entirely on where you stand relative to the black hole's pull. The event horizon itself is often described as the point where space-time becomes so curved that even light rays bend back upon themselves. The geometry becomes so twisted that any path forward, any possible trajectory through space and time, leads inward. There are no paths that lead outward. There is no escape direction. The fabric has been warped so completely that escape becomes a direction that does not exist. Imagine a landscape where every valley, every depression, every path in every direction leads deeper into a ravine. There is no upward, there is no level ground. Everywhere you could possibly go leads down. That is what the event horizon represents for space and time combined. Some physicists and mathematicians like to speak of the event horizon in terms of information and causality. From our outside perspective, no information can ever travel backward from inside the event horizon. Whatever falls in is sealed off from the rest of the universe, and we can never know what happens to it, never observe it, never communicate with it again. This gives the event horizon a quality of absolute finality, a cosmic silence. It is not merely that we cannot see very deep into a black hole. It is that there is a mathematical boundary beyond which nothing can ever send a signal to us, ever again. The universe itself has drawn a curtain. The event horizon is often imagined as perfectly black, and in a sense it is. No light from within can escape it, but in reality, the event horizon does not emit light itself. It is not hot or cold. It is not made of matter. It is purely geometric, a feature of space-time's shape, a consequence of gravity becoming so extreme that it bends the very arena in which time flows. And yet, just outside the event horizon, in the region called the ergosphere, objects can still orbit, can still observe, can still exist in the normal sense. It is only by crossing that boundary that fate becomes sealed, that the universe as you know it transforms into something so alien that our intuitions fail us. In your mind's eye, you might picture approaching a black hole slowly, drifting downward through layers of space-time that grow increasingly curved, increasingly warped. The stars above seem to dim. Your clocks, compared to a friend at great distance, begin to tick more slowly. The sky itself takes on strange colors, shifted and brightened by relativistic effects. And as you approach that invisible line, time grows stranger and stranger, until at last the event horizon appears not as a barrier, but as a threshold, a place where past and future have somehow switched places, where the inward direction becomes the only direction that exists. And once crossed, time no longer flows forward in the usual sense. The singularity itself becomes not a place in space but a place in time, a moment in your future that you will inevitably reach, just as you reach tomorrow inevitably in the ordinary world. Imagine now a moment of profound strangeness. An astronaut has volunteered for the most perilous journey imaginable, a deliberate descent toward the event horizon of a black hole, while a dear friend remains in orbit at a safe distance, watching with instruments and telescopes and a heart full of concern. What unfolds between them is not a simple story of courage and sacrifice. It is a tale of time itself becoming a wedge between two observers who once shared the same hours, the same rhythms, the same experience of duration. The astronaut begins the fall. Inside her spacecraft, she feels nothing unusual at first. This is a profound truth about freely falling through space-time. There is no sensation of acceleration, no G-force pressing her into her seat. She passes through layers of curved space-time as gently as a swimmer gliding deeper into still water. Her instruments tick steadily. Her heartbeat remains calm. Her clock, let us call it Clock A, measures the passage of time exactly as clocks have always measured it. 1 second follows another, with the familiar rhythm of reliability. She is, from her own perspective, in no hurry. Time feels normal because, in her reference frame, it is. But the friend in orbit is witnessing something altogether different. This friend, let us say, has an identical clock, call it Clock B, that ticks at the same rate as Clock A did when both observers were side by side. And now, as the astronaut descends deeper toward that faint glow of gravitational intensity, the friend begins to notice something unsettling through increasingly sensitive instruments. Clock A is slowing down. From the friend's vantage point, which is farther from the black hole's immense pull, time itself appears to be running backward in terms of speed. Each second of Clock A takes longer to arrive as information traveling back to the friend's location. The ticks become separated by longer and longer intervals. The hands move with a sluggishness that grows more pronounced with every kilometer of descent. Here is where the mystery deepens into something almost dreamlike. The astronaut feels nothing. She is utterly unaware that her time is running slower in the eyes of her friend. Her own consciousness, her own biological rhythms, her own sense of duration are all slowing at the same rate as her clock. Everything about her experience remains internally consistent. She could look at her watch and see nothing amiss. She could count her heartbeats and find them perfectly regular. There is no reference frame within her own falling experience by which she could detect that time has changed. And this, quietly, is the heart of Einstein's great insight. Time is not something universal and absolute, broadcasting itself from some cosmic master clock. Time is something local. Time depends on where you are. The friend, meanwhile, begins to experience a creeping sense of isolation. The astronaut's radio messages, which once arrived with a certain rhythmic frequency, begin to stretch out. Minutes pass between transmissions that once came every few seconds, and the astronaut, in her own experience, is transmitting at the same rate she always has. She is speaking 1 word per second, but those words are arriving at her friend's location with increasingly long silences between them, as if the universe itself is drawing out her voice into something deeper, slower, sadder. What happens at the event horizon itself is the culmination of this divergence. As the astronaut approaches that ultimate boundary, her time appears to the distant observer to slow down asymptotically. That is, it approaches stillness but never quite arrives. A clock observed from far away would seem to freeze at the moment the astronaut crossed the horizon. The astronaut herself would appear to hang there, suspended in place, her image fading to darkness as the light from her falling body redshifts toward invisibility. To the friend, it would seem to take an infinite amount of time for the astronaut to cross that threshold. An eternity would pass at the distant location before the astronaut disappeared. But, and this is perhaps the strangest part of all, the astronaut would experience something entirely different in her own reference frame. She would cross the event horizon in a finite time. If she did not look behind her as she fell, she would notice nothing special at the moment of crossing. There would be no jolt, no sudden rupture, no sensation of finality. Only later, as she continued to fall toward the singularity at the center, would the tidal forces, the difference in gravitational pull between her head and feet, begin to stretch her body in what physicists rather brutally call spaghettification. But that is another story, a later chapter of pain and physics. The profound separation between these two experiences reveals something fundamental about the nature of time itself. It is not a stage on which events occur, as Newton imagined. It is a dimension interwoven with space, bent and shaped by the presence of mass and energy. And it can be experienced differently by different observers depending on their motion and their location within a gravitational field. Time is not one thing shared by the universe. It is many things, countless personal experiences of duration that each observer carries with them, diverging and reconverging in a landscape of curved space-time. From the astronaut's internal perspective, her journey is finite and traceable. She might fall for an hour of her own time before reaching the singularity. From the friend's perspective, those same events are stretched into an infinite duration, the astronaut forever frozen at the edge, never quite disappearing. Both observers are correct. Both are describing real aspects of the same event. The asymmetry is not an illusion. It is the actual structure of space-time revealing itself in the presence of extreme gravity. And this asymmetry means that time, at its deepest level, is not something universal and objective. It is something relational, something that depends utterly on where you stand and how you are moving through the cosmos. Yet perhaps the most compelling proof that time itself bends comes not from elegant thought experiments or the distant collapse of stars, but from the ordinary technology that guides us through our daily lives. Every single time you use GPS to find your way through a city, to navigate a hiking trail, or to track the precise location of anything on Earth, you are relying on a system that absolutely requires Einstein's predictions about time. Without the correction for gravitational time dilation, your GPS would place you 30 kilometers off course within just a single day. 30 kilometers. The margin of error would grow so rapidly, so relentlessly, that the entire system would become useless within hours. This happens because the GPS satellites orbiting Earth high above the atmosphere are in a region of weaker gravitational pull than we are on the ground. Time flows slightly faster for them up there than it does for you. Additionally, those satellites are moving at tremendous velocities relative to our position on Earth's surface, and motion, as Einstein showed us, also causes time to move more slowly. These two effects work in opposite directions. The satellites experience time moving faster due to being in a weaker gravitational field, but slower due to their orbital speed. The gravitational effect wins out, and the net result is that a clock on a GPS satellite ticks about 38 microseconds faster per day than an identical clock on the ground. 38 millionths of a second. It sounds impossibly small, almost negligible, like a whisper in an empty room. But electromagnetic signals travel at light speed, and in 38 microseconds, light travels more than 11 kilometers through the vacuum of space. That's the entire error margin we would accumulate every single day without the correction. And so the engineers who built GPS didn't build it as a curiosity or an afterthought. They baked relativity directly into the system, making small adjustments to the satellite clocks before launch, accounting for time's own variation across the landscape of space-time. The beauty of this is that we don't have to accept it on faith. We can measure it ourselves. In 1971, two physicists named Joseph Hafele and Richard Keating performed what might be the most elegant experiment of the late 20th century. They took cesium atomic clocks, the most precise timekeepers humanity had created to that point, and flew them around the world on commercial airliners. One clock traveled eastward, one westward, and one remained stationary on the ground as a reference. The clocks on the planes experienced both the effects Einstein had described. They were moving relative to the Earth's surface, which should slow their ticks slightly. But they were also at high altitude, in a region of weaker gravity where time should flow faster. The physicists had predicted, before the planes took off, exactly how much each clock should drift, compared to its earthbound twin. When the airplanes landed and the clocks were compared, the measurements matched the predictions almost perfectly. The moving clocks had aged imperceptibly, but measurably less than the stationary one. Time, it seemed, was listening to Einstein's equations. Since then, more precise experiments have repeated this finding over and over, each one peeling back another layer of verification. In 1985, physicists used cesium clocks on two separate flights, one heading east, one heading west, and confirmed the effect once more. In 1999, a team used hydrogen maser clocks, even more precise than cesium, to measure the difference between a clock at sea level and identical clocks at higher altitude. The higher clocks ticked faster, exactly as predicted. In 2010, scientists placed atomic clocks on jets and once again measured time's responsiveness to motion and gravity, refining the measurements to unprecedented accuracy. And yet, perhaps the most striking confirmation came with something far more stationary. Consider two atomic clocks, nearly identical, separated only by the difference in elevation. One sits at the bottom of a tower, the other at the top. The elevation difference need not be dramatic. 100 meters is enough. The lower clock sits in a slightly stronger gravitational field. Its time runs fractionally slower. Atoms oscillate at a rate determined by quantum rules, and those rules are written into the fabric of space-time itself. In a stronger gravitational field, the very rhythm of atomic vibration becomes slightly sluggish. You can feel it happening, in a sense, if you could somehow perceive the quantum realm directly. Place an extremely precise atomic clock at the bottom of a 100-meter tower. Place an equally precise one at the top. Let them tick for long enough, and the higher clock will have accumulated more tick marks than the lower. The lower clock will have aged slightly less. This is no longer a thought experiment. It's been done, and the result confirms Einstein's prediction. The difference grows with the strength of gravity, grows with the velocity of motion. Near a black hole, where gravity becomes almost unimaginably intense, these effects amplify to the point where the distinction between the time experienced by an observer falling into the darkness and the time experienced by someone watching from a safe distance becomes an abyss. We live, in other words, in a cosmos where time is not a constant. It is a texture, a landscape, shaped by the very mass and motion that surrounds us. Every technology that depends on precision, nuclear power plants, power grids, telecommunications networks, the very systems that keep our modern world synchronized, all of them run with the quiet acknowledgement, built into their code and their hardware, that Einstein was right. Time bends, time slows. Time is, fundamentally and irreducibly, a part of the universe's geometry, no less malleable than space itself. Imagine two siblings, born on the same day, in the same hospital, their first breaths drawn within moments of each other. Their lives unfold in parallel for decades. They share birthdays, anniversaries, the slow accumulation of wrinkles and silver hair. But what if one of them stepped into a spacecraft and journeyed toward a black hole while the other remained on Earth, watching from afar? The mathematics of relativity allows for something that seems to violate every intuition we hold about fairness and the flow of time. One twin could return to find themselves decades younger than their sibling who never left. This is the twin paradox, one of the most unsettling thought experiments in all of physics. It seems impossible, almost like a violation of nature itself. How could two people, starting from identical places in time, end up with such dramatically different ages? Yet the answer lies not in magic or deception, but in the very fabric of space-time itself, shaped by motion and gravity in ways we are only beginning to truly understand. Let us walk through this slowly, with care. The twin who remains on Earth experiences time as you and I do. The years pass with familiar rhythm. seasons turn. Calendars are marked. They age in the normal way, their body accumulating the small changes that time brings. The deepening of lines around the eyes, the slight stiffening of joints, the gradual shift in how their body feels beneath them. Perhaps 40 years pass, perhaps 50. They grow older with each sunrise. The traveling twin, meanwhile, embarks on a trajectory that carries them toward the black hole. But here is where gravity and motion combine in a way that bends the very sense of duration. As their spacecraft accelerates toward that distant black hole, two things happen simultaneously. First, the velocity of their journey causes special relativistic time dilation. They are moving at an enormous fraction of light's speed, which means their clock ticks more slowly relative to the stationary observer on Earth. This alone is disorienting. But then, as they venture closer to the black hole itself, they enter a region where gravitational time dilation becomes profound. The closer they approach to that event horizon, the more severely the passage of their time is stretched and compressed relative to the observer watching from afar. Imagine standing at the edge of an infinite well, dropping a stone and watching it fall. The stone does not vanish instantly, but from your vantage point on the rim, its descent seems to slow. The further it falls, the more time appears to dilate, as if the stone is traveling through increasingly thick air, struggling against greater and greater resistance. This is not quite the right image, but it captures something true about the experience of falling into a black hole's gravity. The traveling twin, from their own perspective, experiences nothing unusual. They do not feel time moving differently. If they wear a watch, it ticks at the normal rate in their own frame of reference. They might spend what feels like 10 years traveling toward the black hole, hovering near its event horizon, and then returning to Earth. From their internal experience, a decade has passed. They have aged 10 years. But on Earth, something extraordinary has occurred. While the traveling twin felt only 10 years elapse, 50 years have passed on Earth. The stationary twin has aged 50 years. They have grown old. Perhaps they have grandchildren. Perhaps they have watched those grandchildren grow as well. And when the traveling twin returns, stepping out of their spacecraft and embracing their sibling for the first time in decades, they are confronted with a person who has aged at a fundamentally different rate. They are now 40 years younger than their own brother or sister. This is not a matter of perspective or relativity of simultaneity. The clocks have genuinely measured different amounts of time. The traveling twin has experienced less aging. Their cells have divided fewer times. Their hair has turned grey less. The biological clock that marks our passage through life has ticked more slowly for them. This is the extraordinary consequence of gravity and velocity combined. The paradox gains its name from an ancient puzzle. If one twin ages faster than the other, which one is really aging faster? Does acceleration resolve it? Does gravity? The answer, which physicists spent considerable effort understanding, is that there is no paradox at all when we account for the asymmetry. The twin who remained stationary on Earth was in a single, unaccelerated frame of reference for the entire journey. The traveling twin had to accelerate to leave Earth, accelerate again to approach the black hole, and accelerate once more to return home. That acceleration breaks the symmetry. It is real, measurable, and it accounts for why one twin ages less than the other. Near a black hole, this effect becomes almost unimaginably extreme. The deeper you venture into the gravity well, the more pronounced time dilation becomes. It is not linear, it is not gentle. As you approach the event horizon, approaching the speed at which not even light can escape, time's passage slows to a crawl from the perspective of a distant observer. An astronaut could spend what feels like a year in the vicinity of a black hole's event horizon and return to find that centuries have elapsed on Earth. Everyone they knew would be long dead. The language might have changed. The species itself might have evolved or vanished. This is not speculation about distant futures or hypothetical scenarios. The mathematics is sound, the physics is well established. It is one of the most reliable predictions general relativity makes, and it reveals something profound about the nature of time itself, that duration is not absolute. It is not a universal constant that flows the same everywhere. It is woven into the fabric of space-time itself, shaped by the presence of mass and the speed of motion. Two people, starting together, can accumulate different amounts of time simply by choosing different paths through the universe. The thought experiment of the twins illuminates what might seem like a cold and mechanical truth, but there is something deeply human in understanding it. Time is perhaps our most intimate experience. We feel its passage in our bones, in our memory, in the slow transformation of our bodies. To recognize that time itself is malleable, that it can be stretched and compressed by gravity and motion, is to touch something fundamental about existence. The twin paradox shows us that the universe does not grant everyone the same duration, the same number of heartbeats. What you experience depends on where you are and how you move through space. And so we are left with a quietly unsettling thought as we drift through these ideas. If time is truly this flexible, truly this dependent on the specific circumstances of our journey through space, then perhaps the universe is telling us something about the nature of experience itself. We all age at different rates, not just by choices we make, but by the simple geometry of the world we inhabit. What remains behind all these observations and experiments is a profound mathematical architecture, not in the sense of cold numbers arranged on a page, but rather as a deep logic woven into the fabric of reality itself. The equations that describe how time dilates near a black hole are, in essence, poetry written in the language the universe actually speaks. Einstein's field equations, and you need not memorize them or even see them written, capture something almost sensory if you allow yourself to feel it rather than calculate it. They describe the way massive objects curve space-time around them, the way that curvature influences how time flows, how gravity emerges not from a mysterious pulling force, but from the simple geometry of a warped landscape. Imagine, for a moment, that gravity is less like an invisible hand reaching out, and more like the gentle depression you create when you rest your fingertip on a stretched rubber sheet. Now imagine that the rubber sheet is not something separate from space and time, but is space and time itself. Every mass, every star, every black hole creates an indentation in that sheet, and time flows differently along the slopes of those indentations. In the deepest valleys, where the curvature is most extreme, time runs slower. On the high plateaus, far from any mass, time flows at its most ordinary pace. This is not a metaphor. This is the actual structure that the mathematics reveals. The Schwarzschild solution, named after Karl Schwarzschild, who found it just months after Einstein published his general relativity theory, describes this landscape perfectly. Inside that solution, hidden in its elegant symbols and notation, is a description of space-time around a non-rotating black hole. What the mathematics preserves, what it contains like water held in cupped hands, is a precise relationship between distance and the slowing of time. The closer you drift toward that impossible point of infinite density at the center, the more dramatically the rate of time's passage changes. At the event horizon itself, that mathematical boundary of no return, something extraordinary happens. Time's flow approaches zero in the eyes of any distant observer. The equations tell us this with absolute authority, as if they are simply reading back to us the rules of existence. But here is where the mathematics reveals something almost merciful. While those equations are precise and utterly unforgiving in their implications, they also contain a kind of symmetry, a balance that speaks to something deeper than numbers. The very structure that makes time slow near a black hole also means that the infinite density at the center exists in a strange mathematical realm that our current understanding cannot quite access. The equations break down at the singularity, as if the universe itself is protecting some final secret, refusing to let us see all the way to the bottom of that infinite well. What physicists have discovered through decades of mathematical exploration is that this same principle, that massive objects curve space-time and time flows at different rates depending on where you are in that curve, applies everywhere. It is not unique to black holes. It is the fundamental language of gravity itself. The equations whisper the same truth whether we are examining the space around Earth, around the Sun, or around the most massive black hole yet discovered. Space-time is not a stage upon which events occur. Space-time is not a background. It is the stage, the background, and the actors all woven together into one fabric, and time is woven directly into that fabric. When you consider the mathematics this way, not as dry calculation, but as a description of how reality actually organizes itself, you begin to sense something almost mystical in the equations. They are not imposing rules from outside. They are describing how nature simply is. Mass curves space-time. Space-time tells mass how to move. And time, that most intimate and mysterious dimension of our existence, bends and stretches according to the geometry it encounters. It is slower in deep gravity wells because the curvature is stronger, the landscape steeper. And that relationship, that beautiful, relentless relationship between curvature and temporal flow, is what the mathematics preserves and describes. What the equations also reveal, when you allow yourself to feel their implications rather than merely reading their symbols, is that we humans, moving slowly and weightlessly near a planet of modest mass, experience time in a very particular and peculiar way. Our experience of time as smooth and universal, and the same for everyone everywhere, is a kind of optical illusion, a local truth that only holds because Earth is not dense enough to create severe distortions in space-time. We are perched on the gentle slope of a very shallow gravity well, and from that shallow slope, the deeper wells of the universe, the black holes, the neutron stars, the cores of massive stars, seem distant and foreign. But the same mathematics applies, the same truth holds. Time itself is not what we have always intuited it to be. There is also something the equations preserve about the nature of horizons themselves. The event horizon of a black hole is not a physical barrier, not a wall or a membrane you could touch. It is a mathematical boundary, a region in space-time where the equations themselves declare that no light, no signal, no information of any kind can escape outward. It is defined entirely by the geometry, by how dramatically space-time curves in that region. And that geometry creates the consequence that time appears to freeze at that boundary. From the outside looking in, clocks appear to tick slower and slower as they approach the horizon, approaching infinite slowness as they reach it. The mathematics captures this with a kind of inevitability that feels almost like compassion, as if the universe is revealing the consequence of its own structure. In a very real sense, the mathematics is the map, and what it maps is nothing less than the deepest architecture of existence. The equations do not invent these truths, they uncover them. They reveal what was always there, waiting to be expressed in human language, waiting to be understood by a species intelligent enough to look carefully at starlight and time and begin to ask why they behave the way they do. And in that unveiling, in that slow revelation of how time is actually woven into the geometry of mass and space, we find something that touches not the calculating part of our minds, but something deeper. We find wonder at the elegance of it all. And yet, here we arrive at the threshold of something that even our most careful instruments and our most elegant mathematics have not fully revealed. What happens at the very center of a black hole, that infinitely dense point we call a singularity, remains one of the great unsolved riddles of modern physics. It is not for lack of brilliance or effort that we do not know. Rather, it is because our equations themselves seem to break down, to become unreliable, to whisper their limitations at the very place where we most wish for certainty. Picture, if you will, an observer falling inexorably toward the event horizon. We have traced their path through space-time, watched how their clock slows to a crawl in the eyes of their distant companion. But what becomes of them as they cross that threshold and continue downward? Our mathematics tells us one thing, that they will eventually reach the center, the singularity, where all the mass is compressed into a point of infinite density. And yet the same mathematics also breaks into something incoherent at that point, something that refuses to yield clean answers. General relativity, that magnificent framework that has explained so much about the bending of space-time, suddenly throws up its hands. This is where quantum mechanics enters the picture, hovering at the edges of the story like a second voice in conversation. You see, Einstein's gravity speaks the language of the very large, the cosmic, the smooth and flowing. But at the heart of a black hole, densities and energies become so extreme that the quantum world, the realm of the impossibly small, the uncertain, the probabilistic, must surely matter. These two great pillars of modern physics, gravity and quantum mechanics, do not naturally speak to each other. They contradict. They refuse, at present, to be unified into something whole. And that contradiction becomes most acute, most urgent, at the singularity of a black hole. Some physicists wonder whether the singularity is truly infinite at all, or whether quantum effects might somehow regulate it, softening what seems like an infinite point into something merely extremely dense but still finite. Others speculate that the singularity does not actually exist inside the black hole in the way we have imagined it, that perhaps information, as it falls in, is somehow preserved in ways we have not yet conceived. This question has a name, the black hole information paradox. It asks, very gently but with profound implications, what happens to the information encoded in matter and energy as they disappear beyond the event horizon? Does that information truly vanish from the universe? And if it does that not violate one of the deepest principles of quantum mechanics, the principle that information cannot be destroyed? These questions linger in the minds of physicists as unresolved tensions, as problems that invite rather than repel curiosity. Stephen Hawking, in a profound turn of thinking near the end of his life, suggested that perhaps information does not vanish, but is instead scrambled, encoded in ways so subtle and distributed that it might be retrievable, in principle, from the radiation that falls away from the black hole. But even this idea remains contested, uncertain, a bridge being built across a canyon whose far side we cannot quite yet see. The nature of time itself at the singularity, that too remains mysterious. We have followed time as it slows and bends and stretches near a black hole's immense gravity. But at the singularity, where density becomes infinite and our equations collapse, what happens to time? Does it end? Does it become meaningless? Does the very concept of temporal flow cease to apply? There are hints, suggestions from various theoretical frameworks, loop quantum gravity, string theory, other exotic frameworks still being developed, that space-time itself might not be continuous and smooth at the smallest scales, that it might be woven from something more fundamental than what we have observed. But these remain, at present, still in the realm of serious speculation rather than confirmed understanding. Consider also the question of what it truly means to say that time freezes at the event horizon. From the perspective of a distant observer, we have described this as an optical effect, a consequence of time dilation becoming infinite. But there is something genuinely strange here, something that touches the nature of simultaneity itself. For the distant observer, the infalling object appears to take infinite time to reach the event horizon. Yet we know from the perspective of the object itself that it crosses in finite proper time. Which view is correct? Both are true, yet they seem to suggest that the event horizon exists in a kind of temporal limbo, neither fully inside nor outside the stream of cosmic history as the distant observer experiences it. And what of the information that falls into a black hole? If a book falls in, is its content somehow preserved in the geometry of space-time inside? Is it encoded in gravitational waves? Is it stored in ways that our current physics simply lacks the vocabulary to describe? The universe, it would seem, does not discard information lightly. But black holes have long appeared to be the exception, the cosmic trash bin where information goes to be irretrievably lost. Whether this intuition holds or fails remains an open question, one that touches something fundamental about the nature of reality itself. There is something almost meditative about sitting with these uncertainties, about allowing your mind to rest in the space where our knowledge ends and mystery begins. Physics progresses not by having all the answers, but by asking ever more precise questions, by setting up ever more exquisite experiments and observations to test the boundaries of what we think we know. The black hole, with its event horizon and its hidden singularity, remains one of nature's greatest teachers in this regard, a place where the laws we thought were universal reveal their limitations and invite us towards something deeper, something we have not yet fully grasped. The truth, stated as softly as it can be stated, is that at this moment in human history, we simply do not know what truly happens at the deepest point of a black hole. We have frameworks, perspectives, ideas ranging from the highly mathematical to the frankly speculative. But a complete answer, an understanding that satisfies both the demands of general relativity and quantum mechanics, that explains information and singularities and the true nature of spacetime at infinite density, that remains beyond our current reach. And there is something humbling, something almost restful, in that admission. It means there remains work to be done. It means the universe still holds secrets. In the end, what the black hole teaches us is perhaps the most profound revision of human understanding since we first learned to ask what time is at all. For thousands of years, we imagined time as a river flowing past us, constant and indifferent, the same everywhere in the cosmos, whether we stood beneath a village clock tower or watched the stars wheel overhead from a distant mountain. It felt absolute, it felt true, and for the rhythms of human life, that intuition served us well enough. The sun rose, the seasons turned, the heart beat its steady measure, and we moved through a world where moments felt the same everywhere, if only because we had no way to know otherwise. But the black hole, in all its terrible simplicity, reveals something far stranger and far more beautiful. Time is not a river at all. It is a landscape, a geography shaped by the presence of mass, bent and curved and pooled, like water collecting in the low places where gravity is strongest. Near a black hole, that landscape becomes almost unimaginably warped, folded back on itself, and in those folds, time moves at a different pace depending on where you are. Not because the universe is chaotic or inconsistent, but because mass and motion actually sculpt the very fabric in which time flows. The closer you approach the event horizon, the deeper you descend into the gravity well, the more slowly your clock ticks relative to someone floating far away in the gentler regions of space-time. It is not that time is running out faster or slower in some arbitrary way. It is that time itself has become part of the geometry of the universe, woven inseparably from space and gravity. This is what Einstein glimpsed in his imagination when he thought of a falling man, free from the grip of gravity, yet somehow still held. He understood that gravity was not really a force pulling downward, but rather the shape of space and time themselves, bending in the presence of mass, and time, which we thought was the one thing we could trust to be absolutely, universally the same, turned out to be as flexible as space. They were not separate. They were not even two things. They were aspects of a single whole, space-time, a unified fabric that curves and stretches and deepens like an immense landscape of possibility and moment. The black hole stands as the ultimate expression of this truth. It is what happens when mass compresses so densely that space-time becomes so severely curved that light itself cannot escape, and time's flow becomes so extreme that from a distant observer's perspective, time seems to freeze at the edge. Yet if you were somehow to fall through the event horizon, your own experience would unfold in something like normal time, moment by moment, the strange curvature revealing itself only gradually as tidal forces pulled at your body. This paradox, that time is both frozen and flowing, both universal and local, is not a failure of our understanding, but rather a window into how the cosmos actually works. It is elegant, it is precise, and it is utterly humbling. We have tested these truths not in grand cosmic observations alone, but in the quiet precision of laboratories on Earth. Atomic clocks placed at slightly different altitudes tick at measurably different rates. Clocks aboard orbiting satellites must be corrected for relativistic effects, or GPS would fail us within hours. The mathematics that predicted these effects decades ago, emerging from the notebooks of a young man dreaming in thought experiments, has been confirmed again and again in experiment and observation. Time near the Earth, near any mass, really does pass more slowly the deeper into the gravitational field you go. The effect is tiny in our gentle neighborhood of space, but it is real, undeniable, woven into the very operation of our most precise technologies. And yet the black hole teaches us something even deeper than the flexibility of time. It teaches us that beneath all motion, all change, all the rushing forward of moments, there is a structure, a landscape. The universe is not merely happening, it has a shape. Time does not simply flow like a river carrying us along. Time pools and eddies and accelerates and slows according to the geometry around it, and that geometry is determined by where mass and energy have chosen to gather. To contemplate this is to understand that the universe is not a mechanism, like the clockwork that Newton imagined. It is something far more intricate. It is a structure of being, where time and space and matter and motion are all expressions of a single underlying reality. Perhaps this is what makes the black hole such a profound teacher, despite, or perhaps because of, the fact that we cannot enter one and return to tell what we have learned. It exists at the edge of our knowledge, at the boundary where general relativity becomes so extreme that even our most advanced theories falter and hesitate. We do not yet know what truly happens at the singularity, at that point of infinite density where space-time itself may dissolve into something entirely new and strange. We do not know whether the information that falls into a black hole is truly lost forever, or whether it is encoded in ways we have yet to imagine. The black hole remains, in many ways, mysterious, but in its very mystery, it has already taught us something essential, that time is not the absolute background against which the universe unfolds. Time is part of the universe. Time is part of the landscape. Time is shaped by mass and motion, and in the deepest gravitational fields, time becomes so dramatically curved that the future and the past take on meanings entirely different from what our everyday experience suggests. As you drift deeper into rest now, you might imagine that landscape, the gentle hills and valleys of space-time around ordinary stars and planets, the vast plains where gravity is weak and time flows freely at nearly the same pace everywhere. And then, somewhere in the distance, the dark place where space itself is so severely curved that time appears to stop, where the landscape becomes almost incomprehensibly steep, where light cannot climb back out. This is the universe we inhabit, not a mechanism, not a river, a landscape. A whole and intricate geometry of possibility shaped by the presence of things and their motion through the dimensions of space-time. And in understanding this, in feeling this truth settle quietly into your mind, like dust settling in a still room, we understand something about ourselves as well. We are not separate from this landscape. We are part of it. Our moments unfold according to the gentle curvatures of space-time around the Earth, shaped ever so slightly by the mass of the planet beneath us and the sun beyond. Our time is not absolute. Our time is particular. Our time is woven into the very structure of the cosmos, and perhaps that is the greatest gift the black hole offers us in the end. Not just a correction to our understanding of time, but a deep recognition that we are not external observers of a universe governed by laws. We are part of that universe, woven into it, moving through its landscape of moment and motion, each of us following our own path through the gentle slopes and curves of space-time, into the quiet darkness beyond.